The James Webb Space Telescope has provided the strongest evidence yet for atmospheric conditions on distant worlds that could support life. Recent transmission spectroscopy observations from TESS's latest sector surveys revealed methane and carbon dioxide in the atmosphere of K2-18b, marking a pivotal step in exoplanet atmospheric analysis. These detections represent more than simple chemical signatures. They indicate active atmospheric processes occurring on a world 120 light-years from Earth. The precision required to capture these molecular fingerprints from such vast distances demonstrates how far our detection capabilities have advanced. What makes these findings remarkable is not just the presence of these gases, but the implications they carry for understanding planetary atmospheres beyond our solar system. The technology responsible for these discoveries operates with a level of sophistication that transforms how we study distant worlds. The silent revolution above our heads. Each night, TESS scans 200,000 stars for transits, while the James Webb Space Telescope follows up promising targets with infrared spectroscopy to decode atmospheric signatures. This coordinated approach has streamlined the process from detection to characterization, creating an observation network that operates across millions of miles of space. When TESS identified the transit of K2-18b, a potentially habitable world orbiting a nearby red dwarf, JWST immediately began atmospheric analysis that revealed crucial details about its composition and potential for supporting life. The precision required for these observations pushes the boundaries of measurement science. Detecting planet atmospheres requires measuring starlight dips at the 0.01% level, variations so small they challenge the limits of current technology. JWST achieves this sensitivity through its advanced infrared capabilities, which captured the first detailed water vapor signatures in WASP-39b's atmosphere. These spectral fingerprints contain all the information needed to determine atmospheric composition, but extracting this data requires instruments that can distinguish between direct starlight and the modified light that has passed through a planet's atmosphere during transit events. Recent algorithmic improvements have enhanced both telescopes' capabilities beyond their original design specifications. TESS received new pointing algorithms that allow it to observe previously inaccessible regions of the sky, while software refinements have increased planet detection yields by improving the identification of subtle transit signals. The James Webb Space Telescope benefits from ongoing calibration improvements that have enhanced its infrared performance, allowing deeper atmospheric analysis than mission planners originally projected. These upgrades arrived at a critical moment when the scientific community needed maximum performance from the existing instruments. The coordination between these space-based platforms has eliminated traditional delays that once separated detection from characterization. When TESS identifies a promising exoplanet candidate, JWST can begin detailed atmospheric analysis within months rather than years. This seamless handoff between instruments creates observation campaigns that provide comprehensive data about newly discovered worlds. The network includes contributions from other missions like Hubble, whose extended operations provide crucial supporting measurements for atmospheric studies. This technological coordination generates data at unprecedented rates. Automated processing pipelines handle the initial stages of data reduction, identifying potential planetary signals and atmospheric features before human astronomers examine the observations. Machine learning algorithms trained on thousands of confirmed exoplanets recognize subtle patterns in stellar light curves that indicate the presence of planets too small or distant for previous detection methods. The processing power required for this analysis has grown exponentially, with some atmospheric modeling calculations requiring weeks of computing time on dedicated supercomputer clusters. The volume of information collected during 2025 represents a watershed moment in exoplanet science. Current data archives contain detailed atmospheric observations for hundreds of exoplanets, compared to just a handful that existed 5 years ago. Each new observation adds to a growing database that reveals patterns in planetary formation and evolution across different stellar environments. The statistical significance of these observations has reached levels where astronomers can make confident predictions about planetary characteristics based on stellar properties and orbital parameters. Processing this information flood requires new approaches to data management and analysis. Distributed computing networks share the computational load across multiple institutions, while cloud-based storage, systems provide worldwide access to raw observations. Automated classification systems sort through thousands of potential planetary candidates, identifying the most promising targets for detailed follow-up observations. The challenge lies not just in processing individual observations, but in combining data from multiple sources to create comprehensive portraits of distant worlds. The quality of atmospheric characterization achieved in 2025 surpasses all previous expectations for exoplanet science. Spectroscopic observations now reveal not just the presence of water vapor and carbon dioxide, but can determine the altitude at which these molecules exist in exoplanet atmospheres. Temperature profiles show how atmospheric conditions vary with height above planetary surfaces, while pressure measurements indicate whether liquid water could exist at the surface. Some observations have detected seasonal variations in atmospheric composition, suggesting active weather systems and climate cycles on distant worlds. Advanced modeling techniques combine observational data with theoretical predictions to create three-dimensional climate models of exoplanet atmospheres. These models predict wind patterns, precipitation cycles, and surface temperatures with increasing accuracy as more observational constraints become available. The most sophisticated simulations can predict how atmospheric composition might evolve over billions of years, helping astronomers identify worlds that could maintain stable, life-supporting conditions throughout their planetary lifetimes. This level of detail represents a fundamental shift from simply detecting exoplanets to truly understanding their potential habitability and long-term evolution. The precision and coordination achieved by current space-based observatories has transformed exoplanet science from a field focused on discovery to one capable of detailed characterization. Each successful atmospheric analysis adds another data point to humanity's growing understanding of planetary systems throughout the galaxy, building toward a comprehensive picture of how common Earth-like worlds might be among the stars. The accumulated observations from this silent revolution above our heads have created a database that reveals patterns and statistics that would have seemed impossible just years ago. The numbers game that changed everything. Statistical analysis of these observations reveals the true scale of planetary abundance throughout our galaxy. The NASA Exoplanet Archive now contains over 5,630 confirmed exoplanets, with a June 12, 2024 update alone adding 33 new planets to bring the total to 5,663 confirmed worlds. This milestone represents more than numerical achievement. It marks the moment when exoplanet science shifted from discovery-driven exploration to systematic characterization of planetary populations across our galaxy. The database grows at such rapid pace that astronomers struggle to keep current with new additions, as confirmation processes that once took years now complete within weeks through automated validation techniques and improved statistical methods. The confirmation process itself has evolved dramatically from the early days of exoplanet hunting, when each discovery required years of painstaking follow-up observations. Modern statistical validation techniques allow astronomers to confirm planetary candidates based on probability calculations rather than direct measurements, provided the statistical confidence exceeds established thresholds. This approach has proven particularly effective for small planets around distant stars, where traditional radial velocity confirmation remains technically challenging or prohibitively time-consuming. Among the thousands of confirmed worlds, a particular subset has emerged that captures the focused attention of habitability researchers worldwide. Super-Earths, planets between 1.25 and 2 Earth radii, now represent over 1,500 confirmed worlds, despite none existing in our solar system. These worlds occupy the size gap between Earth and Neptune, creating gravitational environments and surface conditions that remain largely theoretical since we lack local examples for comparison. Classification systems for potentially habitable planets have undergone substantial refinement based on accumulated discovery data from thousands of confirmed worlds. The conservative habitable zone definition now serves as the primary criterion for habitability assessment, focusing on orbital distances where liquid water could exist on planetary surfaces under Earth, like atmospheric conditions. This refined approach excludes worlds that might support subsurface oceans or alternative forms of habitability that require more speculative atmospheric or geological conditions. 2-700e represents a prime example of the new classification standards identified as an Earth-sized world orbiting within the conservative habitable zone of its host star. This planet joins a growing catalog of worlds that meet multiple criteria for potential habitability, including appropriate size, orbital distance, and stellar characteristics that could support stable surface conditions over geological timescales. The discovery demonstrates how modern surveys can identify multiple potentially habitable worlds within single planetary systems, suggesting that Earth-like conditions might occur more frequently than early theoretical models predicted. Statistical analysis of the confirmed planet population reveals patterns in planetary formation that contradict several foundational assumptions about how planetary systems develop around different types of stars. The frequency of Earth-sized planets in habitable zones exceeds early theoretical predictions by substantial margins, particularly around red dwarf stars that comprise the majority of stellar populations in our galactic neighborhood. These patterns emerge from large sample sizes that provide statistical significance impossible to achieve during the early decades of exoplanet discovery, when each new world represented a unique case study rather than part of a broader population. Rocky planets orbiting red dwarf stars constitute the largest single category of potentially habitable worlds in current catalogs, fundamentally altering how astronomers approach the search for life-supporting environments. Red dwarf systems offer several advantages for habitability studies, including extremely long stellar lifetimes that provide billions of years for biological evolution, close, inhabitable zones that make planets easier to detect and characterize, and high planet occurrence rates that suggest most red dwarf stars host rocky worlds within their habitable zones. The prevalence of multi-planet systems in discovery catalogs indicates that solitary planets like those in our outer solar system represent unusual configurations rather than typical planetary architectures. 6 of the 11 planets confirmed during a single week in May 2025 belong to multi-planet systems, reflecting broader statistical trends that show most stars host multiple worlds in complex gravitational relationships. These multi-planet systems often display orbital resonances and gravitational interactions that can stabilize planetary climates over extended periods, potentially creating more favorable conditions for biological development than isolated worlds subject to chaotic orbital evolution. Current statistical trends suggest that Earth-like atmospheric conditions occur with sufficient frequency to support optimistic projections about finding life beyond our solar system. The combination of appropriate planetary masses, orbital distances, stellar characteristics, and atmospheric compositions creates a statistical foundation for predicting where life-supporting conditions might exist throughout our galactic region. These numbers transform the search for extraterrestrial life from philosophical speculation into targeted scientific investigation with specific observational goals and measurable success criteria. The numerical revolution in exoplanet science demonstrates that worlds capable of supporting life represent common outcomes of planetary formation process rather than rare cosmic accidents requiring exceptional circumstances. This statistical reality suggests that our galaxy contains billions of potentially habitable worlds, fundamentally changing how we understand our place in the cosmic community and the likelihood of discovering life beyond Earth within the coming decades. Yet numbers alone cannot reveal the full story of these distant worlds. The true breakthrough comes from our ability to analyze what lies beneath these statistical patterns, the actual atmospheric compositions that determine whether these planets could truly support life as we know it, atmospheric fingerprints of distant worlds. When a planet transits, starlight filters through its atmosphere, imprinting absorption lines at specific wavelengths that reveal molecular species. JWST's infrared sensitivity lets us detect water vapor at 1.4 micrometers, carbon dioxide at 4.3 micrometers, and methane at 3.3 micrometers with unprecedented precision. The James Webb Space Telescope operates in the infrared portion of the electromagnetic spectrum, where many atmospheric molecules produce their strongest absorption features. Each molecular species absorbs light at characteristic wavelengths, producing a unique spectral signature that functions like a chemical fingerprint, identifying every gas present in the distant atmosphere. The telescope's unprecedented infrared sensitivity allows it to measure these absorption features with precision levels that seemed impossible during the early decades of exoplanet discovery. Recent observations conducted throughout 2025 have identified several exoplanets with atmospheric compositions that reveal complex chemistry. K2-18b, a sub-Neptune located 124 light-years away, shows clear evidence of water vapor in its atmosphere. JWST captured methane and carbon dioxide on K2-18b, the first such direct detections of these molecules in a potentially habitable world's atmosphere. The planet orbits within the habitable zone of its red dwarf host star, where surface temperatures could theoretically support liquid water if atmospheric conditions permit. Spectroscopic analysis reveals atmospheric pressure and temperature profiles consistent with stable weather systems and possible cloud formation. TOI-715b demonstrates another compelling example of atmospheric characteristics discovered through advanced spectroscopic techniques. This super-Earth orbits a nearby red dwarf star at distances that place it within the conservative habitable zone, where liquid water could exist on planetary surfaces. Atmospheric analysis reveals the presence of water vapor and carbon dioxide that suggest active chemical cycles, though definitive confirmation requires additional observations with longer integration times. Precision measurements now enable scientists to determine not only which gases exist in exoplanet atmospheres, but also their relative concentrations and vertical distribution patterns. Advanced spectroscopic analysis can distinguish between trace amounts of atmospheric components and major constituents, providing quantitative assessments of atmospheric composition that inform climate models and habitability studies. The James Webb Space Telescope achieves measurement precision levels of parts per million for major atmospheric constituents, while specialized techniques can detect trace gases at concentrations measured in parts per billion. Advanced ground-based instruments now achieve space-level precision, scouting atmospheres for JWST follow-up observations. These facilities offer advantages in terms of observing flexibility and reduced costs, while providing atmospheric characterization capabilities that complement space-based surveys. Water vapor detection has transitioned from exceptional discovery to routine measurement across multiple exoplanet surveys. Current catalogs include atmospheric water vapor measurements for dozens of confirmed exoplanets, spanning a wide range of planetary masses, orbital distances, and stellar types. The prevalence of water vapor in exoplanet atmospheres suggests that this essential ingredient for life occurs commonly throughout planetary systems, supporting optimistic assessments about the potential for biological activity on distant worlds. High-resolution spectroscopy techniques enable the identification of atmospheric dynamics, including global wind patterns, temperature gradients, and circulation systems that redistribute heat across planetary surfaces. These measurements reveal three-dimensional atmospheric structures that influence surface climate conditions and long-term atmospheric stability. Scientists can now map temperature variations between day and night sides of tidally locked planets, while identifying atmospheric features that suggest active weather systems, including cloud formation and precipitation cycles. Advanced computer modeling combines spectroscopic observations with theoretical atmospheric physics to create comprehensive climate models for distant exoplanets. These simulations predict surface temperatures, atmospheric pressure profiles, and weather patterns based on observed atmospheric compositions and orbital characteristics. The most sophisticated models incorporate radiative transfer calculations, atmospheric chemistry, and three-dimensional circulation patterns to generate detailed predictions about surface conditions on potentially habitable worlds. Seasonal atmospheric variations detected in several exoplanet systems indicate dynamic weather systems that change over orbital timescales. HD-20-9458b shows systematic variations in water vapor abundance that correlate with orbital phase, suggesting atmospheric circulation patterns that transport water vapor between different regions of the planet's atmosphere. These temporal changes provide insights into atmospheric dynamics and chemical processes that influence long-term atmospheric evolution and stability. Cloud detection represents another frontier in exoplanet atmospheric characterization, with several worlds showing evidence of condensation processes that create cloud layers at specific altitudes within their atmospheres. Kepler-7b exhibits a patchy cloud distribution that varies across the planet's surface, while HD-18n-910733b shows evidence of silicate clouds composed of condensed rock vapor in its ultra-hot atmosphere. These observations demonstrate that cloud formation processes operate across a wide range of atmospheric conditions and planetary types. Atmospheric stability analysis reveals that several characterized exoplanets maintain chemical compositions that could support liquid water on their surfaces for billions of years. Long-term stability requires atmospheric compositions that create appropriate greenhouse effects to maintain surface temperatures within the liquid water range, while avoiding runaway greenhouse conditions that would eliminate surface water through atmospheric escape. Planetary atmospheres that achieve this balance demonstrate the potential for sustained habitability over geological timescales. The most remarkable atmospheric discoveries involve planets that exhibit multiple indicators of potential habitability simultaneously. These worlds combine appropriate atmospheric compositions with orbital characteristics and stellar environments that could support stable surface conditions for extended periods. The statistical significance of these discoveries grows as more exoplanets receive detailed atmospheric characterization, building a comprehensive database of atmospheric properties that informs theoretical models of planetary formation and evolution. These atmospheric fingerprints provide the most direct evidence available for assessing the habitability potential of distant worlds, yet they represent only one factor in determining whether a planet could truly support life. The location of these atmospheres within their stellar systems proves equally crucial to their long-term stability. The Goldilocks zone redefined. Stellar radiation alone cannot determine where life might flourish throughout our galaxy. The classical habitable zone concept centered on a simple premise. Planets must orbit at specific distances from their stars where surface temperatures allow liquid water to exist. This narrow band of orbital distances, calculated based on stellar luminosity and planetary surface conditions, define the boundaries where astronomers expected to find life-supporting worlds. Recent discoveries have shattered this restrictive framework, revealing that habitable conditions can exist under circumstances far more diverse than traditional models predicted. Models show that rocky planets with thick carbon dioxide atmospheres beyond traditional habitable zones could maintain liquid water through enhanced greenhouse heating. Greenhouse gases can trap heat and extend the habitable zone outward by up to 50%, transforming frozen worlds into potentially habitable environments. The discovery of atmospheric compositions on distant exoplanets has revealed numerous worlds with substantial greenhouse gas concentrations that could support surface liquid water at orbital distances previously considered too cold for habitability. Kepler-4042b orbits its star at a distance that would place it outside the conservative habitable zone under traditional calculations, yet atmospheric modeling suggests greenhouse effect could maintain surface temperatures suitable for liquid water throughout most of its 112-day orbital period. The planet's mass indicates sufficient gravity to retain thick atmospheres over geological timescales, while its orbital stability suggests consistent atmospheric conditions that could support long-term habitability. Similar greenhouse processes operating at moderate levels could maintain liquid water on planets orbiting well beyond traditional habitable zone boundaries. Tidal heating represents another mechanism that extends habitable conditions to orbital distances far beyond classical zone boundaries through gravitational energy conversion. Planets experiencing strong gravitational forces from nearby massive objects undergo continuous flexing that generates internal heat through friction and compression. This process can maintain liquid water in subsurface environments or even on planetary surfaces, despite receiving minimal stellar radiation, operating independently of stellar heating to create potentially habitable conditions where traditional models predict frozen surfaces. Red dwarf stars, which comprise 75% of the galaxy's stars, host rocky planets in close orbits that TESS finds frequently, making them prime targets for habitability studies. These small, cool stars offer habitable zones that persist for trillions of years compared to the billions of years available around Sun-like stars. The extended stellar lifetimes provide enormous time periods for biological evolution and atmospheric development, while the close and habitable zones make planets easier to detect and characterize through existing observational techniques. K2-18b represents a prime example of red dwarf habitability, orbiting within the conservative habitable zone of its host star at distances that would place it well inside Mercury's orbit around our Sun. The planet receives stellar radiation levels comparable to Earth despite its proximity to the star, while tidal locking creates permanent day and night hemispheres that could support diverse climate zones. Atmospheric circulation models suggest that heat redistribution between hemispheres could maintain moderate temperatures across much of the planetary surface, potentially supporting liquid water in equatorial regions even if polar areas remain frozen. Recent calculations incorporating improved atmospheric models and diverse heating mechanisms suggest that planets can maintain surface liquid water under conditions far more varied than early habitable zone definitions allowed. The revised models account for atmospheric composition effects, orbital characteristics, stellar variability, and planetary geology to create comprehensive assessments of habitability potential. These calculations indicate that traditional habitable zone boundaries represent conservative estimates that exclude many worlds capable of supporting life-sustaining conditions. Thick atmospheric envelopes provide thermal regulation that can maintain stable surface temperatures across wide ranges of orbital distances and stellar radiation levels. The atmospheric mass and composition determine how effectively planets can trap and redistribute heat, with some atmospheric configurations creating stable greenhouse effects that persist for billions of years. High-pressure atmospheres can maintain liquid water at temperatures well below the freezing point under Earth-like conditions, while atmospheric circulation patterns can transport heat from Sun facing to dark hemispheres on tidally locked worlds. Magnetic field protection plays a crucial role in maintaining atmospheric stability around planets orbiting active stars that produce intense radiation and stellar winds. Strong magnetic fields deflect charged particles and prevent atmospheric erosion processes that could strip away greenhouse gases over geological timescales. Planets with robust magnetic field generation through dynamo processes can maintain thick atmospheres even when orbiting close to their stars, preserving the atmospheric conditions necessary for long-term habitability. HD 2794d demonstrates the complexity of modern habitability assessments through its elliptical orbit that carries the planet between the inner and outer edges of its star's habitable zone. The planet's changing distance from its host star creates seasonal temperature variations that exceed anything experienced on Earth. Yet atmospheric modeling suggests that greenhouse effects could moderate these temperature swings sufficiently to maintain liquid water during favorable orbital phases. The 20 light-year distance to this system makes it an excellent target for detailed atmospheric characterization studies that could confirm theoretical predictions about variable habitability conditions. Statistical analysis of confirmed exoplanet populations suggests that potentially life-supporting worlds occur approximately 10 times more frequently than early habitable zone models predicted. This dramatic increase results from the expanded criteria for habitability that now includes atmospheric greenhouse effects, tidal heating, magnetic field protection, and diverse stellar environments. The revised estimates indicate that our galaxy contains billions of potentially habitable worlds, transforming the search for extraterrestrial life from rare event detection to systematic characterization of common planetary environments. The redefined habitable zone concept acknowledges that life-supporting conditions can arise through multiple physical processes operating alone or in combination across diverse planetary systems. This expanded understanding has guided astronomers toward identifying specific worlds that combine multiple favorable characteristics simultaneously, creating a select group of candidates that stand apart from the most promising Earth twins of 2025. 4 worlds have distinguished themselves as the most Earth-like discoveries ever documented by modern astronomy. These exceptional planets satisfy multiple criteria for Earth similarity simultaneously, including appropriate orbital distances, comparable sizes, and atmospheric compositions that suggest conditions suitable for liquid water on their surfaces. Kepler 452b maintains its position as the premier Earth analog discovered to date, orbiting a Sun-like star at distances that place it squarely within the habitable zone where surface temperatures could support liquid water for billions of years. This world completes one orbit every 385 days, remarkably close to Earth's 365-day year, while receiving stellar radiation levels only 10% higher than Earth experiences from our Sun. The James Webb Space Telescope conducted intensive atmospheric characterization of Kepler 452b throughout 2025, revealing water vapor signatures and atmospheric pressure profiles consistent with stable weather systems operating on the planetary surface. Spectroscopic analysis detected carbon dioxide concentrations that suggest active atmospheric chemistry, while temperature measurements indicate surface conditions that could support liquid water across significant portions of the planetary surface. The planet's host star shows characteristics nearly identical to our Sun, including similar mass, temperature, and metallicity, creating stellar radiation conditions that closely match those that have supported life on Earth for billions of years. Advanced stellar evolution models predict that Kepler 452b star will maintain stable energy output for several billion more years, providing ample time for biological evolution if life has established itself on the planetary surface. TOI-700e represents another exceptional Earth twin candidate, measuring approximately 95% of Earth's diameter while orbiting within the conservative habitable zone of its red dwarf host star. The planet's size places it firmly within the range where rocky composition becomes likely, while its orbital period of 37 days indicates close proximity to its star that compensates for the reduced stellar luminosity typical of red dwarf systems. Follow-up observations using multiple ground-based telescopes confirmed the planet's transit signature and refined orbital parameters that demonstrate long-term stability over millions of years. Atmospheric characterization of TOI-700e reveals seasonal variations in water vapor abundance that correlate with orbital position, indicating dynamic weather systems that redistribute moisture across the planetary surface. These atmospheric changes suggest active hydrological cycles involving evaporation, condensation, and precipitation processes similar to Earth's water cycle. Temperature measurements show moderate variations between different regions of the planet, consistent with atmospheric circulation patterns that transport heat from the permanently illuminated day side to the eternally dark night side hemisphere. K2-18b demonstrates the potential habitability of sub-Neptune worlds through its confirmed atmospheric water vapor and methane detections by JWST. This world orbits within the habitable zone of its red dwarf star at a distance of 124 light-years, with a radius 2.6 times Earth's and an orbital period of 33 days. The planet's atmospheric composition includes carbon dioxide alongside water vapor, creating greenhouse conditions that could maintain liquid water despite its larger size and different atmospheric structure compared to Earth. Recent spectroscopic observations reveal atmospheric pressure and temperature profiles that suggest possible cloud formation and active weather systems operating throughout the planet's thick atmosphere. The combination of water vapor, methane, and carbon dioxide creates complex atmospheric chemistry that could support diverse chemical processes, while the planet's location within the habitable zone provides appropriate energy conditions for maintaining liquid water either on the surface or within atmospheric layers. Luton B offers the remarkable advantage of proximity, orbiting a red dwarf star located just 12 light-years from Earth within the boundaries of our immediate galactic neighborhood. This nearby location makes the planet accessible to detailed atmospheric characterization using existing telescopes, while future missions could potentially reach the system within reasonable time frames using advanced propulsion technologies. The planet's location within the habitable zone of its host star creates surface conditions where liquid water could exist, with a radius approximately 1.3 times Earth's and an orbital period of 18.6 days. Recent observations of Luton B using adaptive optics systems on ground-based telescopes have detected atmospheric absorption features consistent with water vapor in the planetary atmosphere. The planet's mass. and radius measurements indicate a rocky composition with possible surface conditions suitable for liquid water, while magnetic field estimates suggest sufficient protection from stellar radiation to maintain atmospheric stability over geological timescales. Systems like TRAPPIST-1 with 7 terrestrial worlds demonstrate how compact architectures can support multiple habitable candidates. These multi-planet configurations provide gravitational stability that prevents extreme orbital variations, while tidal interactions between planets could generate additional heating that extends habitable conditions beyond simple stellar radiation calculations. With thousands of characterized worlds, we can now do comparative planetology to understand habitability across different stellar types. Advanced computer simulations incorporating detailed atmospheric physics, orbital mechanics, and stellar evolution predict that several Earth twin candidates could maintain surface oceans continuously for geological timescales exceeding Earth's entire history. These models account for atmospheric escape, greenhouse gas evolution, and stellar radiation changes over billions of years, demonstrating remarkable resilience in planetary climate systems. Rocky planet density measurements now routinely match Earth's bulk composition, indicating widespread occurrence of terrestrial worlds with similar internal structures and geological processes. These density measurements combined with atmospheric characterization data create comprehensive portraits of distant worlds that rival our understanding of planets within our own solar system. The combination of multiple Earth-like characteristics occurring simultaneously on individual planets provides the foundation for the next phase of exoplanet research, where astronomers search not just for worlds that could support life, but for evidence that life has already taken hold. The hunt for biosignatures. Detecting the chemical fingerprints of biological activity represents the most direct approach to confirming extraterrestrial life. Biosignatures are specific molecular indicators that can only be produced through biological processes, offering chemical evidence of life that cannot be replicated through purely geological or atmospheric reactions. Modern astronomical instruments now possess the sensitivity required to identify these molecular signatures across interstellar distances, enabling researchers to move beyond theoretical habitability assessments toward direct detection of life's chemical fingerprints embedded within exoplanet atmospheres. The simultaneous presence of oxygen and methane in a planetary atmosphere creates one of the most compelling biosignature combinations possible because these gases cannot coexist in equilibrium without continuous biological production. Oxygen serves as a highly reactive oxidizing agent that would quickly convert methane into carbon dioxide and water vapor through chemical reactions, eliminating both gases from the atmosphere within relatively short geological timeframes. The persistence of both gases indicates ongoing biological processes that continuously replenish these reactive molecules, similar to the way photosynthesis produces oxygen while bacterial metabolism generates methane in Earth's atmosphere. K2-18b has emerged as the most promising biosignature candidate, following extensive observations that revealed methane, carbon dioxide, and potentially dimethyl sulfide in its thick atmosphere. The James Webb Space Telescope detected these molecular signatures using advanced spectroscopic techniques that can identify trace amounts of atmospheric gases across the 124 light-year distance to this sub-Neptune world. Dimethyl sulfide represents a particularly significant discovery because this sulfur-containing compound is produced primarily by living organisms on Earth, specifically marine phytoplankton that release this gas during their metabolic processes. The detection of dimethyl sulfide in K2-18b's atmosphere cannot be easily explained through non-biological processes, making it one of the most intriguing potential biosignatures identified to date. On Earth, phytoplankton in ocean environments produce dimethyl sulfide as a byproduct of their cellular metabolism, releasing this gas into the atmosphere where it can be detected through spectroscopic analysis. The presence of this compound in K2-18b's atmosphere suggests possible biological activity occurring within the planet's atmospheric layers or on its surface, though additional observations are required to confirm this preliminary detection and rule out alternative explanations. Phosphine gas represents another potential biosignature that astronomers actively pursue in exoplanet atmospheres, particularly targeting nearby worlds like Proxima b, where detection might prove feasible with current instrumentation. This phosphorus hydrogen compound is produced by anaerobic bacteria on Earth and requires specific environmental conditions to remain stable in planetary atmospheres. The search for phosphine in exoplanet atmospheres creates additional avenues for identifying possible biological activity, particularly when combined with other molecular indicators that suggest active metabolism and chemical cycling processes. Seasonal variations in atmospheric gas concentrations provide dynamic evidence of biological cycles that change over orbital timescales, similar to Earth's carbon cycle fluctuations that result from seasonal changes in plant growth and decay. Several exoplanets now show systematic changes in methane, carbon dioxide, and water vapor abundances that correlate with their orbital positions and seasonal cycles. These temporal variations suggest active biological processes that respond to environmental changes, producing and consuming atmospheric gases in patterns that mirror Earth's biologically driven atmospheric cycles. Water vapor detection combined with other biosignature gases creates compelling evidence for habitability that goes beyond simple temperature and orbital distance calculations. The presence of water vapor indicates atmospheric conditions that could support liquid water on planetary surfaces, while additional biosignature gases suggest active biological processes that require liquid water environments. This combination of water availability and biological activity indicators provides the strongest evidence available for potentially inhabited worlds among the growing catalog of characterized exoplanet atmospheres. K2-18b represents a promising target for biosignature searches due to its location within the habitable zone of its red dwarf host star and its appropriate size for retaining substantial atmospheres over geological timescales. This super-Earth world orbits at distances where liquid water could exist on its surface, while its enhanced mass creates stronger gravitational fields that can retain atmospheric gases against stellar radiation and solar wind effects. Future observations of TOI-715b will search for biosignature combinations that could indicate active biological processes on this nearby potentially habitable world. The statistical significance of biosignature detections continues to grow as more exoplanets receive detailed atmospheric characterization through advanced spectroscopic techniques. Multiple worlds now show individual biosignature indicators, while several planets exhibit combinations of gases that strengthen the case for biological activity. The accumulation of biosignature evidence across multiple planetary systems suggests that biological processes may operate commonly throughout our galactic region, though definitive confirmation requires additional observations with longer integration times and improved instrumental capabilities. Advanced atmospheric modeling techniques now distinguish between biological and non-biological sources of potentially significant gases by analyzing molecular abundances, chemical equilibrium states, and atmospheric stability over long timescales. These models can predict how atmospheric composition should evolve through purely physical and chemical processes, identifying deviations that require biological explanations. The combination of observational data and theoretical modeling creates robust frameworks for evaluating biosignature claims and determining the likelihood of biological activity on distant worlds. Several exoplanets currently display multiple biosignature indicators that cannot be easily explained through non-biological processes alone, creating the strongest evidence yet discovered for potential extraterrestrial life. These worlds combine appropriate atmospheric compositions with environmental conditions that could support biological activity, while showing chemical signatures that suggest active metabolic processes. The convergence of multiple biosignature indicators on individual planets represents a compelling case for biological activity that will drive intensive follow-up observations throughout the coming decade. The search for these chemical signatures has revealed an unexpected pattern in the types of stellar systems where biosignatures appear most frequently, challenging long-held assumptions about which stars provide the most favorable environments for life to develop and thrive. Red dwarf stars, the unexpected havens. Proxima Centauri b stands as the most compelling example of red dwarf planet potential, orbiting the closest star to our solar system at a distance of just 4.2 light-years. This rocky world completes one orbit around its red dwarf host star every 11.2 days, placing it squarely within the habitable zone where surface temperatures could support liquid water. The planet's proximity to Earth makes it an ideal target for detailed atmospheric characterization using existing telescopes, while its location within the habitable zone creates surface conditions that theoretical models suggest could maintain stable climates for billions of years. Recent observations of Proxima b using ground-based spectrographs have detected possible atmospheric absorbers that might indicate the presence of water vapor, though additional measurements are required to confirm these preliminary detections. The planet's mass, estimated at 1.17 times Earth's mass, suggests a rocky composition similar to terrestrial worlds in our solar system. Advanced climate models predict that atmospheric circulation could redistribute heat across the planetary surface, potentially creating temperate regions where liquid water could exist despite the extreme day-night temperature contrasts typical of tidally locked worlds. The statistical significance of Earth-sized planets around red dwarf stars has reached remarkable levels throughout 2025, with occurrence rates suggesting that most red dwarf systems host at least one rocky planet within their habitable zones. TESS observations indicate that approximately 40% of red dwarf stars harbor Earth-sized planets at orbital positions where surface temperatures could support liquid water. This occurrence rate, combined with the fact that red dwarf stars comprise 75% of all stellar objects in our galaxy, suggests that potentially habitable worlds number in the tens of billions throughout the Milky Way alone. The discovery rate of confirmed red dwarf planets has accelerated dramatically, with new confirmations arriving weekly from coordinated observations using space-based and ground-based telescopes. TOS 700e represents a prime example of this discovery trend, identified through TESS transit observations and confirmed through radial velocity measurements that determined its mass and orbital characteristics. The planet's size places it within the range where rocky composition becomes likely, while its location within the conservative habitable zone creates conditions where atmospheric greenhouse effects could maintain surface liquid water. Multi-planet systems of red dwarf stars demonstrate remarkable orbital stability that protects planetary atmospheres and surface conditions from disruptive changes over extended time periods. The TRAPPIST-1 system exemplifies this stability with 7 Earth-sized planets locked in resonant orbital configurations that have persisted for billions of years. 3 of these worlds orbit within the habitable zone, where liquid water could exist on planetary surfaces, while gravitational interactions between planets create tidal heating that could extend habitable conditions beyond simple stellar radiation calculations. Atmospheric retention capabilities among red dwarf planets have exceeded theoretical predictions, with several worlds maintaining substantial atmospheric pressure despite receiving intense stellar radiation. K2-18b demonstrates this atmospheric resilience through its confirmed water vapor, methane, and carbon dioxide detections, indicating active atmospheric chemistry operating under stable conditions. The planet's thick atmosphere suggests that red dwarf worlds can maintain the atmospheric envelopes necessary for climate stability and potential biological activity over geological timescales. The proximity of habitable zones around red dwarf stars creates significant advantages for atmospheric characterization studies through frequent transit events that occur every few weeks rather than the year-long intervals typical of Earth like orbits around sun-like stars. These frequent transits provide multiple opportunities for spectroscopic observations within relatively short time frames, enabling detailed atmospheric analysis that would require decades to accomplish for planets orbiting more distant habitable zones around sun-like stars. Tidal locking effects on red dwarf planets, once considered fatal flaws for habitability, now appear to create potentially stabilizing influences on global climate systems through sophisticated atmospheric circulation patterns. Advanced climate simulations reveal that atmospheric heat transport can maintain temperate conditions along terminator regions where day and night sides meet, while preventing the extreme temperature conditions that would otherwise make these worlds uninhabitable. These circulation systems can create stable climate zones covering millions of square kilometers on tidally locked planets. The extended stellar lifetimes of red dwarf stars fundamentally change the timescales available for biological evolution on orbiting planets. While Sun-like stars maintain stable energy output for roughly 10 billion years, red dwarf stars can sustain consistent luminosity levels for hundreds of billions to several trillion years. This extended stellar lifetime provides unprecedented opportunities for complex biological systems to develop and evolve across time periods that dwarf the entire history of life on Earth. Current detection capabilities have revealed that red dwarf systems represent the galaxy's most abundant sources of potentially life-supporting worlds, transforming statistical calculations about habitable planets from optimistic projections to probable realities. The combination of high planet occurrence rates, extended stellar lifetimes, and favorable conditions for atmospheric retention suggests that red dwarf planets may host the majority of biological activity throughout our galactic neighborhood. These discoveries about red dwarf planet abundance and habitability potential have been made possible by detection methods that operate at precision levels that seemed impossible just years ago, pushing against the fundamental limits of what astronomical instruments can measure across interstellar distances. The technology behind the discovery. The instruments responsible for these breakthroughs operate with precision that transforms theoretical possibilities into measurable realities. Transit photometry achieves sensitivity levels that detect planetary shadows, reducing starlight by merely 0.01% during transit events, enabling astronomers to identify Earth-sized worlds orbiting Sun-like stars at distances comparable to our planet's orbit. This extraordinary precision demands space-based platforms that eliminate atmospheric interference, while maintaining consistent detector performance across observation periods spanning months or years. Modern transit surveys employ sophisticated data processing pipelines that analyze millions of stellar brightness measurements simultaneously, searching for the characteristic dimming patterns that indicate planetary transits. These automated systems distinguish between genuine planetary signals and numerous false positives created by stellar variability, binary star eclipses, and instrumental artifacts that complicate transit detection. Statistical analysis techniques identify periodic dimming events with durations and depths consistent with planetary transits while ruling out alternative explanations through detailed examination of transit shapes and timing variations. High-resolution spectrographs now achieve measurement precision levels that detect stellar motions as small as 1 centimeter per second, enabling gravitational detection of Earth-mass planets orbiting within habitable zones around nearby stars. These instruments require extraordinary stability in both spectrograph design and calibration systems that provide wavelength references for Doppler shift measurements. The radial velocity technique measures periodic variations in stellar motion toward and away from Earth as planets orbit their host stars, creating characteristic velocity curves that reveal planetary masses and orbital characteristics. Machine learning algorithms have revolutionized exoplanet data analysis through automated pattern recognition systems that process observational datasets containing millions of potential planetary candidates. These artificial intelligence systems learn to recognize subtle transit signatures buried within stellar noise, identifying planetary candidates that human analysts might overlook during manual data examination. Neural networks trained on confirmed exoplanet discoveries can classify new candidates with accuracy levels that match or exceed traditional analysis methods, while processing datasets hundreds of times larger than manual techniques could handle. Direct imaging capabilities have progressed from theoretical concepts to operational systems that capture actual photographs of exoplanets in nearby stellar systems, revealing thermal emission and reflected light from worlds orbiting beyond our solar system. These achievements require coronagraphic techniques that suppress starlight by factors exceeding 10 billion, while preserving faint planetary signals that remain after stellar suppression. Coronagraph technology blocks the overwhelming brightness of host stars through carefully designed optical systems that create artificial eclipses, revealing the comparatively dim glow of orbiting planets that would otherwise remain invisible against stellar glare. The James Webb Space Telescope incorporates coronagraphic capabilities that extend direct imaging to longer infrared wavelengths, where thermal emission from warm exoplanets becomes more readily detectable against cooler stellar backgrounds. Advanced adaptive optics systems correct atmospheric turbulence in real time, creating image quality sufficient to resolve planetary companions at angular separations smaller than 1 arc. Second, These instruments employ various suppression techniques, including vortex coronagraphs and phase masks that achieve contrast ratios necessary for direct exoplanet detection. Coordination between space-based and ground-based observatories creates comprehensive observation networks that combine the advantages of different detection methods and observational capabilities. Space-based platforms like TESS provide all-sky surveys that identify planetary candidates across thousands of stellar targets, while ground-based facilities conduct detailed follow-up observations that confirm planetary nature and measure precise system parameters. This collaborative approach maximizes scientific return from individual missions, while ensuring promising discoveries receive intensive study required for complete characterization. Statistical validation techniques analyze probability distributions of potential false positive scenarios that could mimic genuine planetary transit signals, providing quantitative assessments of discovery reliability without requiring additional observational resources. These methods examine stellar properties, galactic positions, and observational characteristics to calculate the likelihood that detected signals originate from actual planetary transits rather than astrophysical phenomena that create similar observational signatures. Validation approaches achieve confidence levels exceeding 99% for many planetary candidates, enabling their inclusion in confirmed exoplanet catalogs without extensive follow-up observations. The integration of multiple detection methods provides unprecedented confidence in exoplanet discoveries while revealing detailed characteristics of distant planetary systems that remain inaccessible through individual techniques. Transit observations determine planetary radii and orbital periods, while radial velocity measurements provide planetary masses and orbital eccentricities. Direct imaging reveals thermal properties, while statistical analysis confirms planetary nature and rules out false positive interpretations. This multi-method approach creates comprehensive portraits of exoplanetary systems that guide theoretical understanding of planetary formation and evolution. Automated survey operations now process terabytes of observational data weekly, identifying thousands of potential planetary candidates that undergo systematic evaluation through standardized analysis pipelines. These processing systems incorporate decades of experience in exoplanet detection while adapting to unique characteristics of different survey instruments and observation strategies. The efficiency of automated processing enables large-scale surveys that monitor hundreds of thousands of stars simultaneously, creating discovery rates that exceed all previous exoplanet detection programs combined. High-resolution spectrographs with resolving powers exceeding 100,000 now allow detection of molecules on small planets, while future interferometer approaches push resolution toward 300,000 and beyond. These technological achievements represent collaborative efforts spanning multiple decades of instrument development, algorithm refinement, and observational technique advancement. The convergence of these advances during the past decade created the current golden age of exoplanet discovery, where Earth-like worlds transition from theoretical possibilities to characterized astronomical objects with measured physical properties. The precision achieved by these detection methods has fundamentally transformed how astronomers approach the study of distant worlds, moving beyond simple discovery toward detailed the race to characterize atmospheres. Atmospheric characterization has emerged as the defining frontier of exoplanet research, transforming the field from a numbers game focused on discovery rates into a sophisticated science dedicated to understanding the chemical environment that surround distant worlds. This fundamental shift reflects the maturation of detection capabilities and the pressing need to move beyond simple planet counting toward meaningful assessments of habitability potential. Modern atmospheric analysis employs multiple coordinated approaches that combine space-based infrared spectroscopy, ground-based radial velocity measurements, direct imaging capabilities, and machine learning processing pipelines to extract comprehensive atmospheric data from distant worlds. The James Webb Space Telescope operates as the primary infrared platform, capturing spectral fingerprints that reveal chemical compositions through molecular absorption lines, while ground-based high-resolution spectrographs provide supporting measurements and long-term monitoring capabilities. Direct imaging systems achieve the contrast ratios necessary to photograph exoplanets directly, revealing thermal emission patterns and atmospheric properties that complement transit spectroscopy data. Machine learning algorithms process these massive datasets automatically, identifying atmospheric signatures and chemical patterns that would overwhelm traditional analysis methods. The precision achieved through these coordinated techniques enables detection of water vapor around 1.4 micrometers, carbon dioxide at 4.3 micrometers, and methane at 3.3 micrometers with unprecedented accuracy across hundreds of light years. Temperature profiling capabilities now extend throughout entire atmospheric columns, revealing thermal gradients that control weather patterns and atmospheric circulation on distant worlds. Pressure measurements derived from spectroscopic line broadening provide crucial constraints on surface conditions that determine whether liquid water can exist on planetary surfaces. Cloud detection represents one of the most challenging aspects of atmospheric characterization because aerosol particles scatter radiation across broad wavelength ranges, creating complex signatures that require sophisticated modeling to interpret. The presence of clouds indicates active weather systems involving condensation and atmospheric circulation processes that redistribute heat across planetary surfaces. Haze formation creates additional complications while providing insights into photochemical processes operating under different stellar radiation environments than those found in our solar system. Atmospheric escape processes determine which planets retain their atmospheric envelopes over billions of years required for biological evolution. High-energy stellar radiation strips atmospheric gases through photoevaporation, while stellar winds create continuous atmospheric loss mechanisms throughout planetary lifetimes. The balance between retention and escape depends on planetary mass, atmospheric composition, magnetic field strength, and stellar radiation intensity, creating relationships that determine long-term atmospheric stability. Chemical equilibrium calculations predict which molecular species should exist under specific temperature and pressure conditions, providing theoretical baselines for interpreting observational results. Deviations from equilibrium predictions indicate active geological processes, photochemical reactions, or biological activity that continuously produces or consumes atmospheric gases. K2-18b demonstrates this complexity through methane and carbon dioxide detections that indicate atmospheric chemistry operating under conditions not represented within our solar system experience. Comparative planetology approaches combine atmospheric data from multiple exoplanets to identify patterns that reveal fundamental principles governing atmospheric evolution across different planetary masses, orbital distances, and stellar environments. This statistical analysis helps distinguish between universal processes that operate on all planets and specific conditions that create unique atmospheric characteristics on individual worlds. The comparative approach provides insights into how atmospheric composition correlates with planetary composition correlates with planetary formationary processes. Detailed climate models integrate observational atmospheric data with theoretical physics to create comprehensive simulations that predict surface conditions, weather patterns, and seasonal variations on potentially habitable exoplanets. These models incorporate radiative transfer calculations, atmospheric circulation dynamics, and chemical reaction networks to simulate complete climate systems operating under alien environmental conditions. The most advanced climate simulations predict surface temperatures, precipitation patterns, and atmospheric stability over geological timescales relevant to biological evolution. Surface condition predictions represent the ultimate goal of atmospheric characterization efforts because they determine whether liquid water can exist on planetary surfaces and create environments suitable for biological activity. These predictions combine atmospheric composition data with orbital characteristics, stellar radiation levels, and planetary properties to assess habitability potential. The development of reliable surface condition models enables targeted searches for biosignatures and guides future observational priorities toward the most promising potentially habitable worlds. The volume of atmospheric data collected during 2025 represents a watershed moment that transforms theoretical possibilities into measured realities. Current archives contain detailed atmospheric observations for hundreds of exoplanets, compared to just a handful that existed 5 years ago. Each successful atmospheric analysis adds crucial data points to humanity's growing understanding of planetary systems throughout the galaxy, building toward comprehensive knowledge of how common Earth-like atmospheric conditions might be among the stars. The precision and coordination achieved by current atmospheric characterization programs has created a database that reveals patterns and statistics about distant worlds that would have seemed impossible just years ago. These accumulated observations provide the foundation for understanding not just individual planetary atmospheres, but the broader implications of what these discoveries mean for our species and our future among the stars. What this means for humanity's future. These confirmed worlds create tangible destinations that transform humanity's long-term survival strategy from theoretical planning into concrete mission development. The identification of potentially habitable planets provides the first specific targets for interstellar exploration rather than abstract concepts that existed only in scientific speculation. Proxima Centauri b orbits just 4.2 light-years from Earth, placing it within range of advanced propulsion technologies currently under development by space agencies and private aerospace companies. This nearby world offers an accessible laboratory for testing interstellar travel concepts and atmospheric analysis techniques that could revolutionize our approach to exploring distant planetary systems. The rapid pace of TESS habitability discoveries has accelerated interstellar mission development beyond all previous projections. K2-18b represents a prime example of how quickly potentially habitable super-Earths emerge from survey data, creating an expanding catalog of specific destinations that justify increased investment in interstellar exploration technologies. Each new discovery adds another potential target for reconnaissance missions while validating the scientific foundation underlying ambitious exploration programs. The statistical reality that Earth-like worlds occur commonly around nearby stars transforms interstellar travel from science fiction speculation into engineering challenges with measurable solutions. Breakthrough Starshot exemplifies how exoplanet discoveries drive innovative propulsion concepts that could reach nearby worlds within human lifetimes. This initiative explores light sail propulsion systems powered by ground-based laser arrays that could accelerate small probes to 20% of light speed, enabling arrival at Proxima Centauri within 20 years rather than the millennia required by conventional chemical propulsion. The project gains scientific credibility through atmospheric characterization data from the James Webb Space Telescope that provides essential reconnaissance information about target worlds before mission launch. These technological developments represent realistic pathways for conducting detailed atmospheric analysis and surface exploration of potentially habitable exoplanets using existing or near-term engineering capabilities. Nuclear pulse propulsion concepts offer alternative approaches for transporting larger payloads to nearby star systems within timeframes that align with human mission planning horizons. These systems could deliver comprehensive scientific instruments capable of detailed atmospheric analysis, surface mapping, and biosignature detection across multiple potentially habitable worlds within single mission architectures. The combination of confirmed exoplanet targets and advanced propulsion technologies creates mission scenarios that transition from theoretical possibilities to engineering projects with specific technical requirements and development timelines. Proxima Centauri b serves as the primary focus for near-term reconnaissance mission planning due to its proximity and location within the habitable zone of the closest star to our solar system. Ground-based observations have detected possible atmospheric absorption, features that could indicate water vapor presence, though additional measurements remain necessary for confirmation. The planet's estimated mass of 1.17 times Earth's mass suggests rocky composition suitable for surface exploration, while its 11-day orbital period creates frequent observation opportunities for detailed atmospheric characterization. Advanced climate models predict that atmospheric circulation could redistribute heat across the planetary surface, potentially creating temperate regions where liquid water could exist despite extreme day-night temperature contrasts typical of tidally locked worlds. The validation of atmospheric compositions on distant worlds provides essential data that informs mission design and target selection for interstellar exploration programs. K2-18b's confirmed water vapor, methane, and carbon dioxide detections demonstrate that complex atmospheric chemistry operates on potentially habitable exoplanets, creating realistic expectations for what reconnaissance missions might discover upon arrival at similar worlds. These atmospheric fingerprints guide instrument selection and mission architecture decisions while establishing scientific baselines for evaluating biosignature potential on target planets. Space policy frameworks now incorporate exoplanet discoveries as primary justifications for increased exploration funding and technology development initiatives. NASA's long-term planning explicitly includes exoplanet characterization as a stepping stone toward interstellar exploration capabilities, while international cooperation agreements provide mechanisms for sharing discovery data and coordinating observation schedules. The European Space Agency has restructured mission priorities to emphasize propulsion technology development and exoplanet reconnaissance capabilities that complement ongoing discovery programs. These policy shifts reflect growing confidence that interstellar exploration represents achievable objectives rather than distant speculation. Atmospheric characterization techniques developed for exoplanet research generate immediate applications for understanding Earth's climate evolution and environmental monitoring capabilities. High-resolution spectroscopy methods that identify trace gases in distant atmospheres enhance greenhouse gas monitoring and atmospheric pollution detection systems on our own planet. Machine learning algorithms designed to process exoplanet atmospheric data improve climate modeling accuracy and weather prediction systems that support agricultural planning and environmental management initiatives. These technological developments represent substantial returns on space exploration investment through direct applications to terrestrial challenges. The statistical evidence emerging from thousands of confirmed exoplanets suggests that potentially habitable worlds occur commonly throughout our galactic neighborhood, fundamentally altering humanity's cosmic perspective. Red dwarf systems, which comprise 75% of all stars, host rocky planets within their habitable zones at occurrence rates approaching 40% based on current survey data. This prevalence implies that billions of potentially life-supporting environments exist within our local galactic region, transforming discussions about extraterrestrial life from speculative possibilities into statistical probabilities that could manifest as confirmed discoveries within current human lifetimes. The transition from theoretical speculation to targeted scientific investigation represents a watershed moment that establishes realistic foundations for humanity's expansion beyond our solar system. Current atmospheric discoveries provide the essential reconnaissance data required for planning interstellar missions while addressing fundamental questions about habitability conditions throughout our cosmic neighborhood. These achievements create the scientific and technological groundwork necessary for humanity's next evolutionary phase as a species capable of reaching other worlds, guided by observational evidence rather than speculation about what we might find among the stars. The discoveries documented throughout 2025 represent a fundamental shift in how we understand planetary systems across our galaxy. Over 6,000 worlds have been characterized through coordinated observations, with JWST and test collaboration ushering in an unprecedented age of atmospheric study that transforms distant planets from statistical entries into chemically analyzed worlds. The precision achieved by current instruments means that locating biosignatures on distant Earth analogs is now within reach, creating realistic possibilities for confirming extraterrestrial life within the current decade. These technological achievements position humanity at a unique moment where the search for life beyond Earth transitions from theoretical speculation into targeted scientific investigation, guided by observational evidence from thousands of confirmed worlds. What discovery from 2025 excites you most? Share your thoughts in the comments below, and don't forget to subscribe for more updates on humanity's greatest